Today's webinar is a joint presentation with IBM, and we will have two speakers presenting. The first speaker today is Mythili Venkatakrishnan, who is a Distinguished Engineer at IBM, leading the IBM Z Digital Core and Z Compute Grid initiatives. Mythili is also the IBM Z CTO for the financial services sector. Following Mythili, our second speaker today will be Nikita Ivanov, who is the founder and CTO of GridGain Systems. Nikita has over 20 years of experience in application development, building high-performance computing systems and middleware platforms. And with that, I will turn it over to Mythili to start the presentation.
Thank you, Venkat. Thank you. Clients across many industries are responding to business pressures and opportunities with digital transformation initiatives. These efforts can certainly provide significant value to an organization in terms of increased ability to meet competition from non-traditional entities, reduced operations risk, and increased flexibility to address regulatory demands. This particular example is banking focused, but clients in other industries such as insurance are also seeing shifts in their businesses with trends such as movement from product to client-centric focus, a drive to create new products quickly, and the growth of packaged claim systems. Although digital transformation can yield significant positive results, the initiatives can be very broad, and in some cases, the types of transformation required need to be underpinned by changes in how new business functions integrate efficiently and effectively with core systems of record that run mission-critical operations. For example, if we look at the banking space, our enterprise clients are looking to implement more open architectural approaches in order to achieve flexibility to change components based on need, more modular interfaces to decouple point-to-point dependencies to increase rate and pace of new application development, and at the same time evolve to industry-aligned architectures, such as buy-in for the banking industry. As they implement these principles, our clients are also very clear on the need to avoid negative disruption in terms of performance and availability of core systems, to ensure appropriate modularization for purposes of transactional consistency, and the need to have an agile and more simplified information flow between components. Let's explore the need for information flow as differentiated from data flow in a bit more detail. Today, there are core systems, many of them mission critical, that process both transactions as well as batch. These core systems generate high volume and high value data across many different formats in many different contexts. Also today, there exist a number of implementations, both processes and tools to move the raw core systems of record data to various targets. These could be warehouses, data lakes, and other stores of raw data. And the movement of the data can be done at various levels of consistency. While the physical format of the data and access mechanisms may be changed, the content of these stores is generally raw data, having the same context in which it was created on the core transactional systems. There are also applications that do need the full scope of raw data and leverage one or more of these data stores. Examples can include existing reporting apps that may be written to specific warehouse technology interfaces, AI model training that might need significant amounts of granular raw data, and archiving functionality. In addition, over the last few years, there have emerged data virtualization technologies that enable access of raw data in place, and some of these applications can leverage virtualization functions. As clients increasingly evaluate clouds of choice as part of transformation strategies, today they can implement cloud-native applications that use one or more of the full copies of raw data that likely exist in their environment, or they can move the raw data to cloud environments, or they can use virtualization techniques to access the raw data of core systems if possible, or they can invoke APIs to transaction managers for the required data. However, we're hearing from clients that these techniques alone are not sufficient for the speed with which they desire to create new applications in the cloud, since many times there's still a dependency on the underlying context of the data. For example, if there are 7 raw data elements that are computed upon using specific logic in order to produce the relevant account status or balance, this dependency would need to be embedded in the logic and code of multiple cloud-native applications which need the resulting information. In addition, we're hearing that there's a need to leverage more event-driven approaches, where the events consumed by cloud apps are not matched one for one with every transaction from core, but rather an aggregation and mediation of a set of events to determine if and when a cloud app should take action. Also, the data that needs to be used to derive information may in fact come from a variety of transactional as well as batch data and files. Clients that have initiated transformation strategies want to achieve agility and to avoid introducing the multi-data source specific coupling into new cloud apps. The Digital Integration Hub can help to address these needs when it's well integrated with systems of record. The Digital Integration Hub is a representation of information that is derived from one or more data sources. Technology-wise, the Digital Integration Hub consists of a computation engine, an efficient in-memory store for that information, along with a mechanism for integration with the core systems of interest. The Digital Integration Hub also enables the consuming cloud-native applications to decouple, not just from specific data formats, but from the underlying logic of how the specific information needs to be computed. Not all applications need the same level of data consistency or currency, and the Digital Integration Hub enables ability to tune the information instance appropriately. Governance and auditing of information is key, and in being able to have separately managed instances of information used in a many-to-many approach by cloud applications decreases the overall risk posture for the organization. The Digital Integration Hub is not a full replacement for a full copy of raw data. Rather, it can be a highly valuable business operational component to facilitate flexible flow of information with hybrid clouds of choice when implemented in a way that's well aligned with core systems. Now, clients across a number of industries, but certainly a large percentage in the financial services sector, run their businesses on the IBM Z Platform. For example, 44 of the top 50 banks and 2/3 of the Fortune 100 leverage IBM Z. Mission-critical systems such as credit card processing, demand deposit account management, claim systems, tax processing, investment services, bank treasury services, and many more run at very high levels of scale on IBM Z. Most of the enterprise clients that run their core systems on the platform leverage and rely specifically on the z/OS operating system, taking advantage not only of the performance and reliability of the hardware itself, but leveraging the high-value, unique abilities of the entire stack, including the numerous capabilities and services in the operating system, such as the ability to have a fully coherent, consistent data sharing environment, which in turn is tightly integrated with middleware and databases for unparalleled HA and DR at scale. These applications generate extremely valuable raw data, both from transactions as well as batch operations. A Digital Integration Hub on IBM Z can provide a differentiated and unique value for those use cases where integration with core systems is valuable. Specifically, the combination of efficient in-memory techniques, optimally integrated with highly performant data virtualization and access, can deliver scale and low latency with minimal impact to core operations. Since many of the systems of record operate on IBM Z, there's also reduced complexity in terms of aggregating and computing on the right data to deliver the necessary information and the ability to decouple cloud-native apps from specific data contexts. As clients expand their omni-channel use, there's an increasing unpredictability of workload characteristics that can impact core systems. Leveraging a Z Digital Integration Hub enables clients to mitigate that impact, while at the same time taking advantage of an efficient interaction with core systems. In addition, aggregating and processing high-volume transaction events, providing efficient mediation, and then emitting the right granularity of events for cloud applications or a consuming ESB can result in a much more efficient mechanism for communication between core systems and cloud applications. With an efficient Z Digital Hub integration, clients can benefit from a faster business return on investment for transformation, increased agility to expand to new channels and partners, as well as the ability to leverage their high-value investments within the organization. The Z Digital Hub Integration Hub is an offering that delivers ability to create context-specific in-memory instances of information, where that information can be derived from one or more sources of data. The optimized in-memory instances are based on GridGain Enterprise for ZOS, which is an in-memory compute platform built on the in-memory Apache Ignite database foundation. GridGain for ZOS offers a Java-based in-memory environment that is ACID compliant, offers full SQL support, and runs efficiently and performantly natively on ZOS. Application components within the Z Digital Integration Hub leverage the ZOS Java runtime support, as well as GridGain for ZOS. The GridGain Ignite instances integrate via fast local sockets with the data virtualization component, which in this case is the IBM Data Virtualization Manager for ZOS, called DVM for short. On ZOS, fast local sockets are implemented as memory-to-memory communication, providing a highly optimized communication path. In addition, for some specific and unique application or industry formats such as ACH or ISO 8583 for card, DVM may be able to leverage additional industry templates and extensions that are being developed by Rocket Software, who is one of IBM's business partners. The DVM capability provides a highly parallel and optimized access to a wide array of data sources on IBM Z as well as off-platform. In addition, for some use cases relative to DB2 ZOS and IMS, there's the ability to read the underlying data sets directly to further minimize impact to core transactional systems. The instances of the Z Digital Integration Hub can also be clustered for throughput, scale, and HA. There can also be separate instances based on use case for auditing and governance purposes. In addition, the content of the in-memory instances can be persisted to disk, in fact, to a database such as DB2 ZOS for DR reasons. Cloud-based components can then leverage the instances of the Z Digital Integration Hub via a variety of interfaces, including REST, JDBC, or event-based flows using Kafka. Note that this does not eliminate the necessity for interaction with transaction managers as needed via direct APIs to core systems such as CICS or IMS. Those are directly enabled via REST-based APIs as well. And depending on the usage scenario, cloud components may interact directly with transaction managers or with the Z Digital Integration Hub. Now, the content of the in-memory instances are not just a cache, but in fact a full SQL compliant database that's able to be updated. For example, new tables can be created, which are derived from information coming from one or more Z Digital Integration Hub instances. However, the underlying raw transaction or batch data is not updated outside the context of the driving application within the core system, and that's to ensure consistency and coherency of the overall transactional environment. In addition to cloud-based components, core systems applications may also directly interact with instances of the Z Digital Integration Hub, and we have discussed use cases with clients where that might be valuable. Now let's look at a few scenarios where the Z Digital Integration Hub can provide value. In this example, we look at the value of providing a holistic view of client, where the client can be an individual or perhaps a small or medium enterprise. In many cases, organizations have grown through acquisition in siloed architectures, and integrating these environments in the context of a client view can be challenging. While the front-end application that supports 360 view of client or business may be deployed in a cloud environment, a Z Digital Integration Hub can offer clients the ability to link the underlying disparate systems and do so in a way that's flexible in terms of what information is surfaced, how often additional types of information are needed, as well as the agility to quickly adapt the environment for new cloud applications. This type of use case can be applicable across a multitude of scenarios, but certainly increased ability to cross-sell or quickly determine the total value of the client to the business is a key advantage. We know that many of our enterprises are expanding their ecosystem of partners, specifically in the RegTech space, to amortize the cost associated with the increasing number of regulations and increasing rate of change of these regulations. As an alternative to exposing raw data from core systems to a RegTech, or enabling an API for every interaction that the RegTech may need, clients can leverage a Z Digital Integration Hub with separately managed and audited instances for each RegTech, where the instances would contain the specific information that a given RegTech needs in order to conduct business. For example, if a RegTech needs information relative to cards, derivatives, cross-border payments, then the bank can continually aggregate just the relevant information in an instance of the Z Digital Integration Hub and surface that information via APIs or push via events. In addition to RegTechs, the same information flow pattern can be leveraged for other ecosystem partners in the compliance and risk arena, such as those focused on anti-money laundering. The variation would be in what information is needed to be surfaced, at what currency, and using which interfaces. In this example, the bank runs their core banking application on IBM Z, on ZOS, performing standard demand deposit account management, as well as ACH and wire processing. The data generated by core systems is in a specific application context, and the data itself is stored in vSAN. In this environment, there's a payments decisioning application that is hosted off the Z platform, which may in the future be deployed in hybrid cloud. A couple of times a day, raw data, which is in an application-specific format, is transmitted to the payments app. The payments application then computes on that data, and it needs to have the knowledge of the application-specific context of the data in order to perform its computations. And then it derives a relatively small subset of information elements that it then needs in order to communicate with external payment service providers. In the future state, the Z Digital Integration Hub will efficiently integrate the output of reconciliation from overnight batch, which will be in the form of another set of vSAN data, as well as the payload of intraday transactions. The logic in the instance of the hub will then join these sources and produce results, which is roughly 25 or less elements of information. These results then get streamed to a payments decisioning application via Kafka. The outcome is not only a much more efficient flow of just the information that's needed via event-based techniques, but also decoupling and increased flexibility for the consuming application, as well as much more currency of information that contributes to the overall payment decision. Almost every client we speak with is pursuing core modernization of some kind, and the range of strategies varies widely. In many cases, although the technology capabilities of the underlying Z platform have continued to evolve and offer a rich set of options, the applications themselves have not been modified in 20 or more years. This can lead to point-to-point interactions, data contexts that are embedded in logic and unavailable for metadata functions, and of course, delayed insight. Specifically in the financial services arena, the vast majority of clients are looking at progressive modernization approaches, where there are incremental enhancements to core systems and assessments of which capabilities may be able to leverage cloud effectively. There are also a variety of paths that clients are taking for modernization, and these are not mutually exclusive by client or even by application. For example, clients are looking at opportunities to identify the right granularity of function, modularize these functions, introduce APIs to integrate with cloud-based functions, and rewrite those modularized functions as appropriate. In addition, there have been significant enhancements in DevOps processes and tool chains over the last couple of years, and clients are retooling to take advantage of these and to expand the overall skill base. Introducing an agile and flexible information flow with the Z Digital Integration Hub as part of the overall modernization process is another potential path forward that provides some advantages in the overall modernization. In some cases, there's often a fairly lengthy time frame of coexistence expected as clients modernize the existing core apps. The related data formats and contexts will be in place during this period. Even as select components may be deployed in clouds of choice, these will still need to exchange information with core systems. And the Z Digital Integration Hub can provide an optimized interaction capability. In addition, the Integration Hub can provide a shorter-term return on investment since the approach does not require the application and data modernization to be completed prior to deriving the business benefit. In addition to the ones we've discussed, there are other use cases with similar patterns that we've discussed with enterprise clients. The overall pattern of combining batch output with relevant core transactional data that's produced intraday and then deriving the right set of information to make available either via events or APIs is the key theme. In addition, channel applications do often need information at the edge for increased business value and function. But often clients are trying to do this today with capabilities that are focused either on accessing or moving of raw data, rather than making the necessary information available via an efficient flow. Last but not least, across multiple types of interaction, our enterprise clients are expanding their ecosystem partners. We've seen this specifically with omnichannel as well as compliance use cases, but there are many examples where an effective ecosystem will need efficient integration with core systems of record information. Now, specifically on IBM Z and ZOS, there are a number of advantages to the Z Digital Integration Hub. There is, of course, the performant and efficient access to the data and transactional environments, resulting in both scale and currency of that information. There's the ability to integrate these functions in a manner that's attractive with respect to total cost of ownership, leveraging IBM Z's specialty engines. There's an ability to have improved security by first determining the right information to surface and then auditing that information access. Clients can derive a greater degree of overall governance and control. Z clients often have highly effective, thoroughly tested, and reliable DR strategies. The ability to leverage IBM's DB2ZOS for persistence of in-memory information as needed enables clients to leverage their existing investments in well-proven DR tools and processes. And lastly, the information in the instances of the Z Digital Integration Hub is usable and useful not only for cloud components, but also for applications that are hosted on IBM Z. The Z Digital Integration Hub instances can communicate with those core environments in a highly optimized manner. From the previous examples and the details presented, you can see how a digital integration hub can be essential to transformation. And in addition, how an efficient integration of such a digital integration hub with core systems on IBM Z can deliver even more value for the enterprise. Now over to Nikita to discuss the value of in-memory techniques and compute to create effective digital integration hubs.
All right, Venkat, let me know if you guys can see my screen.
Yep, it's not the full screen. Right. Can you make it the full screen mode?
Why don't we keep this way, by the way?
Okay,
it's probably
sounds good.
A little bit better. Yeah, because I may be jumping from slide. So Mythili, thank you very much. And so my name is Nikita Ivanov, and I'm from GridGain. And since we only have about 10-15 minutes for this portion, what I'm going to do is I'm probably going to talk a little bit more about in-memory computing in general, and I'll kind of dive into the GridGain and what it is in the Android, just to give you an example of technology. But I really want to kind of emphasize the value of in-memory computing and how it arrived to where it is today. I've been involved with memory computing for the last almost 20 odd years. And I've seen this transition from very early stage in the late 90s, all the way to where we have today. Now, in-memory computing is an interesting topic. It's, whether you're technical or not, you almost can, intuitively sense what it's all about, right? Anybody who's involved with computers for the last 50 years know that, memory is pretty fast and the other type of storage is pretty slow. And when we talk about memory computing, intuitively we can understand that, if we move data from slow storage to the fastest storage, which is RAM, things generally go faster. And that's the claim of the performance and scalability. But there's a lot more to the story that sort of meets the eye initially. And that's what I want to basically pinpoint, so that we have a little bit deeper understanding of why it is. First of all, about the speed, you're absolutely right. And your intuition is right, that when you move data from slow storage to memory, things go fast. What most of us don't realize is how fast. I've been doing this presentation for many, many years. Probably the best explanation I found is that if you would consider the speed of RAM as the speed of a jet fighter, then a speed of your typical spinning disk or even some flash devices would be like banana slag in your garden. That's the dramatic gap in difference in speed. So that's kind of, a basics of sort of economics behind memory computing. Things in memory go dramatically faster. But as we discovered in late 90s, that was just the beginning of a story. In memory computing has a lot of wrinkles to it. And one of the wrinkles was that obviously we're not going to have as much RAM as we have disk space. Just economically impossible. Sometimes back in those days was technically impossible. So you could have a many gigabytes of disk space back in those days, and even later on. But you can only have very small portion of that as RAM. So from very early days of memory computing, the memory computing practitioners had to develop systems that would string together many computers together, because that was the only way to get enough RAM to really store, practical amount of data that's required by your applications and systems. So, unbeknownst to many in industry, in memory computing was one of the first and one of the most advanced distributed systems in existence, and to this day. Quite frankly, there's only a few systems in the world, and I'm talking about systems by projects like Hadoop, for example, like Cassandra, like Apache Ignite, that are known and demonstrated to scale into the thousands of nodes in the coherent cluster topologies. And in memory computing, went this route basically through the need. We had to find a way to have enough RAM to store practical amounts of data, and the only way was to basically do the cluster distributed computing, to string together many computers together and to use this common memory pool. Now that in of itself really branched in memory computing, not only to idea of, hey, let's just store things in RAM close to CPU, but hey, since we have that distributed environment, why don't we dive into the parallel processing? And that's a very important and oftenly overlooked property of the memory computing systems, of any modern series of memory computing systems, such as GridGain, for example. That is a combination of in-memory storage and a massive parallelization of processing. Now, there's a lot of terminology around this. I'm not going to bore you with this, but again, we usually talk about in memory computing giving you both speed and scale. That's not a marketing talk. That's actually a very technical definition. You get speed by moving data from disk to RAM, and your access to this data, which I'll talk in a second, will get dramatically faster. But that in of itself doesn't give you a scale. The scale comes from parallelization. Since most of the memory computing systems of any practical size are distributed systems, you are gaining this parallelization or effect on your processing. And systems like GridGain basically, they're essentially can be viewed as a kind of two systems in one. It's one about storing data in RAM across multiple computers. Another one is doing a very comprehensive modern parallel distributed processing. Now, another interesting kind of caveat is that I often get asked, why is that storage in memory is so much faster? It sounds, especially the flash. I mean, everybody understands the difference between tape drive and a RAM. That's obvious. Most of the people even understand the difference between spinning disk, your traditional, hard drives, and RAM. But what about flash? Why is flash so much slower on average? And the explanation is a little bit technical, but I can basically give you a glimpse on this. So think about what needs to happen when there's basically two explanations. One is very technical, just literally I can explain. Another one is a little bit tricky and less technical. The first technical is very simple. Think about what needs to happen in an operating system when you need to load a byte of information from RAM and let's say from an external drive, such as flash. So when you need to load from flash or disk or tape, doesn't really matter, you have to go through an entire stack of calls in the operating system, from application to application API to system, operating system API to the driver, and the driver basically interacts with potential operating system, and then it goes back to actual device. And device basically has a seek time, it finds the particular byte, and then this byte has to travel all the way back to the same stack of calls to the application that made a call. If you compare that path with what happens in memory, it's very striking. In memory, all you have to do is just to do pointer arithmetic. You just have to change the address at which essentially you're pointing your code, and that's it. So in terms of memory, it's typically nanoseconds, maybe microseconds. When it comes to external devices, it could be 1,000 times more, just because of that long stack call. And that's the essence of the speed. Where we're getting the speed from, but that's not the whole story. Another dramatic difference between in-memory storage of data and storage on external disk is the fact that the economics of acquiring data is very different. And it's based on the fact that most of the external storage is a block level device, while memory is a byte addressable. Let me explain it in a second, very quickly. So the block level device essentially is when you need to read 1 byte of information, you have to read the entire block. And the block typically is 2 or 4 kilobytes. So when you need to read 1 byte, you have to read sometimes 4,000, you need to read 4,000 bytes. Out of those 4,000 bytes, you have to discard almost all of them and keep 1. That's extremely inefficient, but that's how the block devices work. Contrast this with the memory. In memory, you basically just need to read 1 byte. And the cost of reading 1 byte is exactly 1 byte. While cost of reading 1 byte from external devices is cost of reading 4,000 bytes. Now, obviously, if you're reading large amounts of data, that sort of kind of washing out. But for a pinpoint transactions for a small data updates, it's extremely inefficient. Beyond just inefficiency, that over the years, if I look over the last 20 years, this difference in the access patterns to the data led to a complete redesign of most of the algorithms that used to access the data, to really take advantage of that. Because not only there's a difference, if you don't take advantage of this difference, you're not getting any speed of performance. And many modern in-memory computing systems, and GridGain is a perfect example of that. We took a great pains in redevelop most of the data access algorithms when it comes to transactions, to processing SQL, to key value, to map reduce, to simple caching APIs. We took full advantage of that discrepancy. Not discrepancy, but this characteristics of a memory system, that the cost of reading just a few bytes is extremely lower than reading the same amount of bytes from the external devices. So hopefully that gives you a little bit of a kind of technical background why in-memory computing is such an important technology in today's world, specifically in applications like in a digital integration house. What I also say often when I speak about this, and it's an interesting kind of a tangential view in this, is that unlike flash, for example, in-memory processing is here to stay. It's essentially a final evolutionary stage in terms of where we store data and how to process. Now it's a grand, it's a pretty bold statement, but when you think about it, it's a pretty accurate statement. I always ask my audience to kind of look back at where we started. in the late 40s, we started with the first hard drive, because we kind of figured out that a couple of hundred bytes or keeping in our memory of those computers was not enough. We have to have funny enough, before hard drives, people were writing down the registry in paper, and that was perfectly fine when you have about 100 bytes storage in those computers. But when things get bigger and bigger, people figure out we need to have external storage, and that's how first hard drives came around. And then since then, those times, we basically rode this wave of technology evolution from tape to hard drives to flash. But when you think about it, it was always a crutch technologically, because the reason we had those external storage systems is because we never had enough RAM, or RAM was expensive, or we didn't know how to address a large amount of RAM in the computer. We didn't have networks, and networks were very expensive. We cannot string computers together, and there was always this technical impediments that to a kind of a clean solution. And a clean solution is to have the CPU and then have the RAM that contains all the data you need. As a matter of fact, that was the classic computer. So it's very interesting to know that the external storage was always a crutch. It's always a temporary solution. And today, when you think about it today, RAM is available. We have networks that are fairly cheap and economical to operate, so we can string together tens and hundreds and sometimes thousands of computers together and very cheaply if we have to. There are mainframes that are massively reliable and massively scalable on the other end. There's a software available, and one of the our original sins of RAM is volatility, right? We all guys know that unplug the power, things in RAM go away. Even that is solved today. As a matter of fact, it's been solved for many years. But today it's solved in a very core level with a non-volatile RAM pretty much becoming available month by month. So when you think about it, the in-memory computing of storage data with memory in memory is essentially the original and a final destination of this technological evolution. Looking for another side, think about what else can you do. Imagine you have a limited budget. What else can you buy that will actually make your data processing go faster? There's nothing to buy. There's nothing to do. Memory will get faster, memory will get more capacity, but fundamentally, that's the end of evolutionary development when it comes to data storage. We finally get rid of the crutch technologies like your disk, your flash devices, and we move into this kind of clean design without any limitations. And there's nothing that on the horizon. As a matter of fact, unless we, and that's not only my thoughts, if you talk to analysts, you will basically hear the same idea, that unless we change fundamentally our understanding of computing, whether it's biocomputing or something else in the future, maybe it's quantum computing, IBM folks would know a lot more about this. There is literally nothing else. So the memory computing is a fundamental technology. It's slow in take because it's kind of complex beast, but it's slowly but surely taken over some of the most critical, mission critical systems. And this is one of those cases where you don't hear it as much, but I guarantee you work in Wall Street, you work in London, and you work in any other areas where mission criticality is important. Almost every company would have something to do with the memory computing. So memory computing actually developed over time, and this is the interesting slide from Gartner. And by the way, I'm going to have just a few slides. Don't worry about the 50 slides I have. I keep those if I have questions. We can dive into this, but just very quickly. The memory computing is, as a category, is really developing. And today we're talking about a memory computing platform. It's really just a combination of many different aspects of in-memory storage and processing. It's in-memory databases. It's essentially a traditional databases with just in-memory engine where you keep data in memory data grids, which is more of a key value transactional stores with the same in-memory capability, whether it's stream analytics and event processing in memory, or any other INC technologies like Gartner puts this, for example, those analytics and just an in-memory file system and whatnot. And just to round it about, just about now, in my opinion, it's all kind of converges into the idea of a memory computing platform. Like, for example, GridGain is a clear example of this technology where you have it's not just a data grid database, it's really a set of APIs, set of capabilities that you don't have to use all of them, but you have a choice to make. It has a fully transactional SQL capability, both read and write, the DML and EDL. It has classic data grid that you can basically build your high performance applications. It has support for streaming analytics. It has support for machine learning and memory and all of that stuff. So that's what really defines a memory computing platform today. Now, let me talk about just a few more minutes about what is GridGain, and we'll switch to Q&A. So GridGain essentially is a memory computing platform. You guys can learn about it. I only have a few minutes. I'm not going to bore you with technical dive-ins, but it's fundamentally based on a Apache Ignite project. And if you're not familiar with Apache, it's the same body. It's Apache Software Foundation that spun up the projects like Hadoop and Kafka and Spark, and Apache Ignite belongs to the same family of projects. It's an open source and free project. Apache Ignite is really one of the top projects in Apache Software Foundation, practically by any measure. And a GridGain essentially plays the same role like typical cloud data will play for Hadoop. We provide you a kind of enterprise version of Apache Ignite with extra features and extra capabilities. So this is the only slide I have about GridGain, and again, it's pretty loaded, but fundamentally what you see here in the red is what's provided by Apache Ignite. And Apache Ignite is a self-sufficient system. It's a great way to start and get to know the capabilities in memory computing. And things in gray is what GridGain brings to the table in terms of the enterprise level features. And those are truly enterprise level features. We're very unique here. We're not just providing support and consulting around the product. We truly developed, and we were original developers of Apache Ignite back in the day. But we also develop, and all of this are enterprise level capabilities when it comes to advanced monitoring management, security and audit, things like segmentation protection, which happens in distributed system. We have very advanced data centric application. We obviously have the we actually work with Z Platform, things like roll and upgrades, backups, and the point time recovery and whatnot. So Venkat, I'm probably going to stop right here. I have obviously plenty of other slides to follow, but I'll keep those if there's any questions on my side. Back to you.
Awesome. Thank you, Nikita and Mythili. That was great. It is now time for the Q&A section of the webinar. Audience, as I mentioned earlier, if you have any questions for the speakers, please enter them in the questions section in the GoToWebinar control panel. All right, let me just... The first question I have is, this one's maybe for Mythili. What is the process to get started with a digital integration hub project?
That's a great idea, great question. So a couple of different things. When we speak with clients, we find that the best option is really to have a combination of roles from the client. So certainly someone that understands the business application, what information needs to flow, and for what use case would be needed. We would want to also have some parts of the core systems team, and if that happens to be on Z, then some of the IBM Z team from the client that understands their data environment. And from an IBM perspective, we actually, through the Z Digital Integration Hub offering, offer a path where we do a series of workshops to help scope out the use case in detail, do the architecture, the flow, the data, the data flows, and really dig into the use case to prove that out. And then we do a pilot to get started. Because the pieces can be complex, and if you look at some of the industry material around Digital Integration Hub, refers to the fact that there are some pieces to integrate, and it can be complicated for clients to just put the technology pieces together on their own. We like to deliver these from an IBM perspective via the pilot, but from a roles perspective, we like to work with stakeholders at the client who are both on the application business side as well as some of the data and IT side to understand what their requirements would be for a successful implementation.
Awesome. I guess another question on industry. Which industries could benefit from this architecture? How widespread is this use case?
Yeah, that's also a very good question. So from an industry perspective, we're certainly seeing a very strong relevance in use cases across the financial services sector. For us, that includes, banking of all kinds, retail, wholesale, as well as investment banking, as well as insurance. We're also at property and casualty insurance, as well as health insurance. There's also relevance in terms of retail, as well as some of the state and federal government examples. Digital Integration Hub in and of itself is not an industry-specific term, but there's a lot of relevance in across FSS, but also in other industries as well.
Cool. One question for Nikita. Can you tell us more about non-volatile RAMs and if that has an impact on the architecture?
Yes. So talking about a non-volatile RAM, there is I'm kind of stumbling a little bit because we've been involved with volatile RAM for the last like 6 years, and we've been up and down in this road. Most of the volatile RAM today, non-volatile RAM, I'm sorry, is really treated as a block level device. Essentially, it's just becoming a disk for your system. And this way, obviously, we support it from day one. For us, there's absolutely no difference what type of disk it is, right? It's NVMe or it's a tape drive. On that scale and range, we don't really care. For us, it's just something that works faster or slower, and we can work with anything. Now, there's a direct mode on Intel Optane that's slightly different. Now, in direct mode, you can actually access on the NVRAM as the byte addressable storage. We're in the process of integrating this in a GridGain, but I think it's going to take the reason we haven't released it yet is because it's probably going to take a couple of more years for the market to kind of saturate it or even penetrate the market so that we can have in the RAM enabled images on most of the cloud providers and many data centers and whatnot. But again, today, if you have any kind of NVMe storage solutions that expose to block level devices, we support them by definition.
Great, thank you. This might be from Mythili, or Nikita, you can also jump in. Are these solutions relevant for data sources such as SaaS applications or streaming data feeds like stock quotes?
I can take a go at that. I think it would be relevant for any data source on which you want to compute and produce information. And so I'm sure Nikita can talk to the streaming capabilities that GridGain and Ignite have, but from the perspective of Z, we're certainly seeing use cases where clients want to combine both data that's that say has been produced and is on disk and is not changing, and combine that with incoming transactions that are streamed through various resources that we have on Z and produce information. So I think streaming data is very viable for this approach. Nikita, do you want to add anything?
Yeah, I don't think it has anything to do with specifically any computing platform, because when it comes to streaming, we're not trying to reinvent the wheel. So for example, in the streaming context, GridGain is often used with Kafka and Confluent solutions generally. But I think the integrated digital integration hub idea is ideally suited for these use cases, because you want to have a highly performant component in your system that is responsible for intake of the streaming data to all the pre-processing, filtering, cleanup, anomaly detections, anything you want to do. You don't want to do it in your core, storage systems, your databases, your Hadoop systems and whatnot. You're just never going to get anywhere close to required performance. So having a digital integration hub in your architecture, by default gives you the right place and the right technology stack to do a modern streaming processing. Yeah, we've seen it many, many times already in multiple, custom applications. So I think the whole idea of Digital Innovation Hub has, direct and ideal application to this use cases.
Great. The next question for Mythili is, would this approach still be applicable for clients that have implemented data lakes and operational data stores?
Yes, it would. Almost all of the clients that we speak with have one or more data lakes and have some other full copies of raw data, perhaps in operational data stores. And they're really meant for different use cases. With data lakes and the such, the applications that use them really have a need to access all of the raw data. And in that case, the continued use of those environments makes sense, right? The Digital Integration Hub is really oriented towards information flow during operations, where that information is computed from the raw data, but not in the same context. And in the examples that we just heard in the previous question, you can really be processing both the data that is static combined with stream data in order to mediate those events in the stream data and aggregate the information to produce results. They're really meant for different use cases, but certainly it's applicable to clients that already have other sources of raw data.
Yeah, I can add a little bit just to this. It's a good question, by the way. We gotta have seen this confusion a little bit, and what I usually say is that if you consider our idea of a high-performance data lake, sometimes it can be a pretty close in what a data integration hub would do for you. It's obviously it's a very malleable definition, so the Venn diagram certainly has an intersection there. But yes, I think generally idea of a data integration hub really evolved from those high-performance data lake applications, where people were getting the subset of data into this different environment and like, I need to have much high performance. I can't really use Hadoop for that. I need something else for that. And then basically, hey, how do I integrate this piece of data with this piece of data? How do I pre-compute them so that my applications have much faster access? And I think that's how the idea of integration hub really evolved from, one of the, ancestors of this idea was the high performance data lakes.
Great. What is the support model for this solution?
I think that's probably for me.
Yeah, I think so.
So the support model is interesting. So we actually initiate the implementation of a Z Digital Integration Hub via the pilot approach that I spoke about earlier. But the support model relative to the products are really, these are GA products, right? So GridGain Enterprise for ZOS is a GA product supported by GridGain. The IBM Data Virtualization Manager for ZOS is also a GA product, and as Rocket software releases industry templates, they will support. So from the componentry of the technology, they're supported by the relative partners that we're working with, as well as IBM. The content of the Digital Integration Hub instances, and maybe I can share my screen here if it's okay, Venkat, to answer this question.
Yes.
Okay, hopefully I could see them. Okay.
Yep, I can see.
So the content in terms of the application logic that would constitute what's in the instance, for example, whether you're combining reconcile batch with incoming transactions, that content is actually an application. And in this context, it would be a Java application shown in the green where you see the GridGain Ignite box. And that application is really owned, by the client. And so while we deliver a pilot to do an initial implementation of the first use case, those are not black boxes to the client. So the client actually owns that application and would continue to maintain it in whatever way. But they would own the IP of that application, can extend to other use cases, etc. The technologies that support that are all GA products.
Awesome. I guess this question may be for Nikita. How much code change would be required to port an existing, siloed application to this architecture?
Good question. And again, we'll get it quite often. So how much? So what's the change that required? It really depends. If your application is heavily SQL and you SQLize the ways to access the data, there could be very trivial change because GridGain itself is a fully SQL 99 compliant platform. Now, on the other extreme, if you have a completely proprietary ways to access data, it may take a while. It may take few weeks of effort. Obviously, I'm guessing kind of averaging out of because you would need to change the way you access the data. So, and we've seen everything from hey, I've changed it overnight and look at this, it's working already, all the way to a several months projects where very significant changes will have to be made to applications to take advantage of that. So again, I wish I could tell you it takes exactly one day and that's it. It really depends. It really depends on the application and the way the application currently is accessing the data.
All right. And maybe the last question for Mythili, and I think this relates to the previous answer. What are the options to keep the instances of the integration hub current? David?
Okay. Yep. Yeah, it's a good question, Venkat. So there are a few options to keep the instances of the Z Digital Integration Hub current, and it depends on the use case. Of course, the currency that's needed really depends on what you are populating that instance with, right? Is it focused on compliance use cases? Are you looking for summary, account summary, et cetera? So many clients today do have change data capture technologies from IBM or others, and these can feed into the data virtualization layer that's part of the componentry on Z. And if the instance uses that data as part of the computations within the Ignite instance, the change data can be streamed to that instance to redrive the computation. In another pattern, there can be transaction payload that's selectively written to a log stream facility on ZOS that we have, and then that can be streamed, again, via the virtualization component to the Ignite instance. And then, of course, there's options to periodically redrive the computation if it's more of an interval approach that's needed to the currency. So there's a few approaches.
Very good. Thanks, Mythili and Nikita. Audience, that brings us to the end of the Q&A section and to the end of the webinar. I'll be sending a follow-up email with a link to the recording and to the slides. Thanks, everyone. Have a good day.